Welcome. This is one of the videos under the Pulp&Fuel Learning package. The topic of this presentation is the work package called Gasification of Solid Biomass. My name is Fredrik Weiland. I'm a research scientist at RI.SE, the Research Institutes of Sweden. I have worked with biomass gasification over the last 15 years or so, mainly in the field of high temperature and oxygen-blown processes, as the one you can see here on this slide, for instance. Our role in the Pulp&Fuel project was therefore the gasification of dry paper mill residues. This means essentially the bark coming from the logs processed at the mill. In this project, two bark assortments were tested, both a softwood bark and a hardwood bark. These feedstocks were dried, milled and pelletized before any further processing. Furthermore, we used two different gasification technologies within the Pulp&Fuel, both a fixed bed technology and an entrained flow technology. The fixed bed is generally good in the smaller scale, whereas the entrained flow concept is essentially the preferred option when it comes to larger scale installations. However, nevertheless, both technologies, they produce a product gas called synthesis gas, or syngas just in short. It is composed of many components, primarily carbon monoxide, hydrogen, some carbon dioxide, water vapor, methane, and some other minor constituents. Carbon monoxide and hydrogen are, however, the most important components or the components of interest when it comes to further downstream fuel synthesis. And the target of this gasification work package was actually to find operating conditions that maximize the yields of these two components. There are many types of gasification technologies. The two types that we tested in the Pulp&Fuel project were the oxygen-blown entrained flow concept and the fixed bed technology. In the entrained flow reactor, the pulverized biomass is fed through a burner where oxygen is added, and the particles are kind of entrained in the gas stream and converted as it goes down the reactor. In the fixed bed technology, pelletized biomass was used. It was fed on top of a bed where oxygen jets were injected from three different locations, one from underneath the bed and at two different levels above the bed. And in the paper from Vinica, we showed that this small-scale pilot gasifier was actually capable of producing a similar gas quality as a much larger entrained flow gasifier when operated on the same fuel. Therefore, most of the experiments in the Pulp&Fuel project was performed in the smaller fixed bed gasifier because it actually required much less resources, both in terms of personnel and consumables. So the project could actually afford more experiments in this type of reactor. The gasifier, the fixed bed, is operated at approximately 20 kilowatts, meaning it corresponds to a bark fuel feeding rate of approximately 4 kilos per hour. When it comes to gasification, this oxygen stoichiometric ratio, denoted lambda, it's the most important controlling parameter during gasification. At lambda equal to 1, we have stoichiometric combustion and we produce only CO2 and water vapor. But as you can see in these graphs, we tested lambda somewhere, or oxygen feeding somewhere in the range from 30 to 60% of what is required for combustion. That means we generated an energetic gas composed of hydrogen, carbon monoxide, and methane, as shown here in the three graphs showing the gas yields. The fourth graph shows what's called the cold gas efficiency. This cold gas efficiency actually reflects how much of your biomass energy content that ends up as chemical energy in your cold syngas. And we can see we had some we found some sort of optimum when we operated the gasifier about lambda 0.4. At lower lambdas, we had the cold gas efficiency was reduced due to a poor fuel conversion, whereas at higher lambdas, the cold gas efficiency was reduced because of excess combustion of the wanted energetic syngas components. So combustion of CO, hydrogen, etc. If you would like to see more and all the results from this work package, it can be found in the research articles referred to down here at the bottom. So to conclude our work, oxygen-blown gasification of bark residues resulted in a very good syngas quality. We generated significant yields of hydrogen and CO. The maximum cold gas efficiency that we measured corresponded to approximately 76%, and it was measured during the test with softwood bark and at lambdas about 0.4. This is expected to improve on a larger scale where the proportion of heat losses becomes less significant than in our small-scale pilot reactor. When it comes to future work, this is partly related to the inorganics contained in the feedstock. It's important to have control of this composition to ensure an efficient ash handling and a efficient ash discharge in any type of gasifier. Furthermore, we believe that advanced diagnostic tools and machine learning can help to further improve the gasification efficiency. This is something we have been started to work on. All right, with that, I thank you for listening, and I hope you have enjoyed this short summary of the gasification work package. Thank you and goodbye.